Today's problem is product of arrays except self. All right, let's have a look, man. So given an array of integer nums, return an array output where output I is the product of all elements of nums except for nums I. Each number is a 32-bit integer, and there's a follow-up where they want us to do it without using the division operator. So let's have a look at an example. So here we have 1, 2, 4, 6, and it becomes 48, 24, 12, and 8. So let's have a look at an example. Let's say nums is 1, 2, 4, and 6, and we can see that the result is like this. So what's happening here? So for the index 0, we're taking the product of all the numbers except that, which is 2 times 4 times 6, and that gives us 48. And then you can see in index 1, it's 24 because it's taking the product of everything except 2. So this times this times this, that gives us 24. And so on and so forth. At index 2, it's the product of 1, 2, and 6, which is 12. And then at index 3, lastly, it's the product of 1, 2, and 4, which is 8. I'm going to introduce two simple solutions. The first solution is simply the brute force solution. Now the brute force is going to look something like this. It'll be a double for loop for I in, for j in, and then I is going to be here, j is going to be here. And then if j is I, then we ignore that number. But otherwise, we take this, the number 2, multiplied by the number 4, multiplied by the number 6, and then we increment I, and then j starts here again. And then is j is equal to I? Nope. Then we have 1 multiplied by, is j equal to I? Yes, then we ignore this. Then we come here, is j equal to I? No. So we take 1 times 4, and then we move j here, 1 times 4 times 6, and then we just continue this. J here, j here, j here, and then we keep doing that for each element. So that's going to be an O of n squared solution, right? Not the most ideal solution, but that's okay. There is a better solution. I know this says that they want us to solve it in O(n) time without using division, but I'll show you the division example, because this one's also pretty simple. Well, relatively speaking anyways. So back to our original example. So if we just took the product of this, we'll get 48, right? And once we have this, we'll loop through each number again, but this time we'll do like 48 divided by 1, 48 divided by 2, by 4, and by 6. And that'll give us the correct answer, right? 48, 24, 12, and 8. Hey, that matches. That's also another simple solution. And the upside of doing this is that we do one loop to calculate the product, and then we do another loop to calculate division thingamajig. And they'll give us the answer. But actually, there are some complex edge cases which make the solution mayhaps not the best. To demonstrate this, we can have a look at the second example here. So looking at the second example, we have -1, 0, 1, 2, and 3. Now, if I calculate the products are going to be this times this times this and this. Obviously, there's a 0 here, so everything is going to be 0. So what happens? Well, then if I do the division step, it'll be everything divided by 0. This will become 0, and then this will be a divided. And then once we get to this point, we will have 0 divided by 0, which is going to throw a divide by 0 exception, and that's not going to work. Well, there are ways around it. We're not doomed. If you notice in this example and the expected output, you'll notice that at every index that is not the 0 index, the result is just 0, because we have a single 0, and that's going to dominate the multiplication. So everything's going to be 0. Okay, so that's not very interesting. So in the case where we have 0, everything's going to be 0 except the index of 0, which is going to be, if you notice, the product of everything else aside from 0 is -6. So -6. So okay, why don't we handle that edge case? We'll say that when we calculate the product, we'll ignore all of the zeros, so we'll go through them one by one, and then we'll ignore the zeros, then we'll get -6, and then all we have to do is find the index of 0, and then once we have this, we can use this to fill in wherever that index was with the product, and then the rest of the slots, we just fill them up with 0. This definitely works. That covers the edge case, but there's one more edge case here. As you can tell, the solution is not looking so good, because we have to deal with a lot of edge cases. And the thing is, because I researched this beforehand, I'm able to tell you these edge cases, but I think as you're solving them, like, these things might be unexpected. So there's one edge case that's not even in example 1 or 2, and that's the edge case where there are multiple zeros. Let's say I replace this 3 with a 0. What happens? Right? We run the same algorithm. What happens? So before running the algorithm, I want to see what the product is supposed to be. So without thinking about how the computer's going to solve this, I'm just going to look at this and go, well, at this slot, the product of everything except this number is 0. The product of everything except this number, well, we have a 0 here, is 0. Now you notice, if there are multiple zeros, because there is another 0 at hand, the product is all going to be 0 anyways. Okay, so let's wrap this up. So for this division solution to work, we need to keep track of how many zeros there are, calculate the product, ignoring zeros, and then we have to handle 3 separate cases. Where in 3A, there are multiple zeros, then return all zeros. Case B, where there's exactly 1 0, then return 0 in all slots, except the index with 0, which will be product. And then case C, which is the normal case, where you loop through nums and do product divided by nums I. Yeah, okay, this works. And it's even O of n time complexity, right? Because you loop once to calculate product, and then you loop one more time to calculate the result. Either way, the follow-up is banning us from using the division operator, so this algorithm doesn't even work. So how are we going to do this then? I'm actually going to take some inspiration from the brute force method. So if you have a look at the brute force method, say we're calculating it for this iteration, where I is here. We basically want the product of everything to the right of I and everything to the left of I, right? But because there's nothing here, it's basically 1, right? And also you could say the same thing about the right side, where we want the product of this, and like nothing here. And then that's the end, right? So I could say that I want the product of 1 from the left times the stuff from the right, which is 2 times 4 times 6 times 1. So I'm being very explicit with this one for reasons that you will see later. So this is for I equals 0. So if I say I equals 1, if I'm calculating for here, for this index, I want all of this and all of this. So we have 1 times 1, and this one is this one, which is the same thing as this. And then I want 4 times 6 times 1, right? Makes sense. 4, 6, and nothing. Let's move on. Index 2. So if I is here, then I want this and this. So 1 times 2 from the left, and 6 times 1 on the right. Now for I equals to 3, I want this and I want this. So it's 1 times 2 times 4 and 1 basically, right? So there's a very specific reason why I laid it out this way. This is going to be the compute from the left, and this is going to be the compute from the right. And effectively, if you want to compute the value, it's just going to be the left portion multiplied by the right portion. You can see that in every single one of this, right? So that's one thing that I want you to notice. Result is equal to the left portion times the right portion. Well, the second thing that I want you to notice is the repeated computations. Repeated computations. So I just want you to focus on the left side for a bit. So for the very first index, it's just 1, right? And for the second index is whatever the previous index had multiplied by I minus 1, right? So if I is here, we want everything that the previous index spat out, and I minus 1, which is this thing. And similarly, we want the previous number, so this, multiplied by all of this, and so on and so forth. And you can see the same pattern on the right, but it's from the reverse. The right side starts with 1, and then takes the compute multiplied by 6, right? And then takes this compute and multiplies it by 4, and takes this compute and multiplies it by 2. So what do we actually do with this insight? So let's say I had a list like this. I'm going to call this result, or res, I guess. 1, 1, 1, 1. Same size as nums. Now, what I'm going to do is that I'm going to have a variable called product left. And this is going to keep track of the product of every element that came on the left. All right, initially it's 1. So let's start with the first index. I is here, I is here. I'm going to have I refer to the same position, 0. So we pose the question, what is the product of everything that came before this index inside our nums? Well, the answer to that question is going to be reflected in this list. So obviously there's nothing before I equals 0. So because of that, the answer is 1, right? The answer is 1. Now, before we move the I to the next index, I want to update this. Because like I said, this is the variable that's going to keep track of the products of every element to the left. To the left of what? To the left of I. So if I is here, I want the product of everything here. So I want this number, but this number happens to be 1, so it's just 1. Okay, pretty boring, right? Not a big deal. So the answer to that question, what is the product of everything to the left of this? It's 1 still. Okay, cool. Now, but here's where it starts to get a little bit interesting, because I have to update this value now. Before we move the I here, so we know that once we move the I to this location, we're going to ask the same thing. What is the product of everything to the left? We're only focused on the left. Well, we know that the product of everything to the left of I is going to be 2. Right, so in preparation of moving this I, we kind of have to update this, right? So initially our product left was 1, and then once we incremented to here, we multiplied that by 1, so that's 1. And then now we multiply it by 2, because once we move to the next index, which we're going to do right now, the product of everything to the left of this is 1 times 2. Aha, there you go. So you can see how this variable is going to keep up. And then now we repeat the same thing. We ask the question, what is the product of everything to the left? Well, we happen to be keeping track of that in our variable, right? So it's going to be this 1 times 2, 2, right? And then in preparation for the next iteration, I'm going to update this again, right? So we're going to multiply it by 4. So by the time we increment I once again, and then we are looking for the product of everything here, we kind of already have that calculated. And the answer is 8. Now obviously, this isn't the final solution yet, but you can see that I basically computed all of this exactly once. I didn't process the number 1 like 4 times here. I didn't process this number 1 3 times. I didn't process this number 2 twice. Every number is read exactly once and computed exactly once. In other words, constructing this list is O of n. But we're not done yet. By doing this, we did save in the repeated computations, but what's the point of that if that doesn't get us to our final answer? Now I want you to have a look at the first point. You see, the result at any I is gonna be the left part multiplied by the right part. See, we've already done this calculation, so all we have to do is perform these calculations in the same way, because you can see it's also formatted the same way, but it's just going from back to front. So if we apply the same principle and we calculate everything once, we'll arrive at the answer once we combine it with the left calculations, right? Sounds pretty solid in theory. Before we move on, I'd like to put what the expected answer is. Well, I guess the expected output. Now that we have it explicitly written out, we can compare it with our answer once we're done. And also, for a little sneak peek, you can already see that our last value, here 8, already matches this. Because looking at this chart, you can see that this is basically the left computation times 1, right? So we've already gotten this down. All right, let's finish it. So I'm going to create a new variable called product right. And this variable is going to hold the product of every element to the right of I. And initially, just like with product left, it's going to be 1, right? Because initially here, well, there's nothing. So the most neutral number that we have in multiplication is 1, because it doesn't change anything. All right, let's apply the same principles. But this time I'm going to move from back to front so we can avoid repeated computations. So let's start with I equals to 3 at this point. So at I equals to 3, well, I is also pointing here. What is the product of everything to the right of I? Well, because it's the end of the list, there's nothing. So 1, right? So we'll go 1 times 8. So 8 doesn't change. All right, cool. Again, before we move on, we have to update this product right, because we're going to be moving this I to the left. And while we're at the left, we want to know what is the product of everything to the right, which is 6 this time. Great. So before we move on, we'll say 1 multiplied by the value of nums I, which is 6. Great. Let's move on. Next iteration. And once we're here, we want to multiply this by everything to the right, right? Because 2 represents all of this. And then now we need to multiply it with this. So the variable that's tracking the product of everything to the right is product right. Great, so we just multiply 2 with 12. Oh, now we can see it's coming together. We got an 8, 8, and now we got a 12. You see? Looking pretty solid. Pretty solid. And of course, as usual, we have to update it by multiplying this value with nums I, which is 4, right? And then we move our I here, and then we want the product of all this, which just so happens to already be stored here. Multiply that value with 1. So 1 times 6 times 4, 24. 24. And then we update this value by multiplying it with nums I times 2. Then I move here to our last position where this seeks the product of all this, and product of all this is already here. And the answer to that is 48. 48. And then we update this by multiplying by 1. But you know, it doesn't matter anymore, right? All right, so running this algorithm is going to cost us O of n a second time, right? So we basically did all this in linear time. And as you can see, it matches. So time complexity is going to be O of n, and space complexity is also going to be O of n because we need this extra space, and this is as long as the size of nubs. And that's the solution. Let's get to coding this thing. Okay, so first up, we want to create our results array, right? Results array was what? A bunch of ones. And how many of those do we want? We want it to be the size of nubs. Okay, so then we want to do the calculations for all the left stuff, right? So we'll make a variable, product left, which is going to keep track of the products of all the elements that we have to the left of I so far. All right, start with 1. And then I'm going to do a for loop for I in range length of nubs. And this is going to go from left to right. Okay, so what's the first step? If you remember, the first step is to multiply results of I with the product of everything that came to the left, which is the value saved in product left. And once that's done, we want to update product left by multiplying it with nums I, just like we did in the whiteboard. Well, that's pretty much it for the left pass. And then I'm going to create another variable called product right. And this is going to be 1. And we're going to do it from the back to the front this time, right? For I in range length of nubs minus 1, minus 1, minus 1. Okay, we're going to take the result of I, and then we're going to multiply that with product right. And then we have to update product right. Right is equal to, well, multiply equals to nums I. And then once that's done, well, the result array should be done. Return result. And that's the code. I think the code itself is a pretty one-to-one representation to everything that we were doing in the explanations. So if you ever feel like you're a bit lost, maybe have a look at the explanations again, because this is just the same thing in code form. All right, see ya.